Okay, a quick video on section 8.3, which follows L'Hopital's rule and is pretty straightforward. First thing you should recognize is a function like e to the x grows very fast as x approaches infinity, whereas something like ln of x grows very slowly. ln of x still goes to infinity, just much more slowly. So the only thing you need to know in 8.3 is we say f of x grows faster than g of x as x goes to infinity if the limit of f of x divided by g of x is infinity, or conversely, if you do the limit of g of x over f of x goes to 0. So that's pretty straightforward. Now this one's a little bit confusing to some people, but we say f and g grow at the same rate if the limit as x goes to infinity of f of x divided by g of x equals some finite number not equal to 0. And the difference is if this happens, then the function is greatly outstripping the other one. If this happens, then it's higher than the other one, but nothing close to what goes on when it's infinity. All right, let me see if I can get this in here. So here's the worksheet. So all you need to do, L'Hopital is going to be your friend for quite a while. I say, does e to the x grow faster than this polynomial? So I look at the limit. It's infinity over infinity, which is one of the allowable scenarios where I can apply L'Hopital. So I take the derivative of the top, and I get 3x squared minus 3, which is still infinity over infinity. I apply L'Hopital again. I get e to the x over 6x. I still have infinity over infinity. Apply it again and get e to the x over 6, which is infinity. Therefore, e to the x is greater than, or grows faster than this function. And as you can see, with any polynomial, I don't care if it was x to the 1,000,000th, e to the x, you're going to continually take derivatives. Eventually, that polynomial is going to get down to a constant. So now, show that ln of x grows slower than x minus ln of x. So I'm going to show that this grows faster by taking the ratio. So this ratio I can immediately break up using the Sam Hooker rule and say that's equal to x over ln of x minus 1. Now the 1 doesn't matter as I grow really large. But x over ln of x, if I look at that, the numerator is going to infinity, denominator, apply L'Hopital, I get 1 over x minus 1, which is the limit as x goes to infinity of x minus 1, which is going to infinity. Therefore, x minus ln of x grows faster than ln of x. Last one to illustrate the thing that confuses people a little, show that these two grow at the same rate. So I look at the limit of x squared plus 4x divided by x squared. I divide top and bottom by the largest power in the denominator. So I get 1 plus 4 over x over 1. This is going to 0, so the limit is going to 1. Therefore, they grow at the same rate. So just to show you, even if I had 10x squared plus 4x, I would end up with a limit that went to 10. As long as it's finite, we can consider them growing at the same rate. That is it for 8.3.